Good afternoon, ladies and gentlemen. I'm Sara Ragazzi, member of the ICAS Executive Committee, and I'm delighted and honored to introduce the speaker for the next general lecture, who is Frank Haselbach. Frank is Head of Propulsion Engineering at Airbus, and in this role he's accountable for end-to-end integration on all propulsion and non-propulsion propulsive power plants at Airbus commercial aircraft. Also, he is responsible for the definition and leadership of technical propulsion power plant strategy for the same company with all internal and external partners, as well as driving the relevant technology and industrial compatibility acquisition program. He is visiting professor at the University of Oxford, holds a doctorate in mechanical engineering, and is also president of ISABE, that is the International Society of Air-Breathing Engineering. So, in the role of the president of ISABE, I now invite the president of ICAS on the stage for a special moment that will be the signature of the Memorandum of Understanding between ICAS and ISABE.
Thank you, Sarah. Thank you, audience. It's a great moment again. I don't know how many of you knew this, but ISABE is actually one of the spin-offs of ICAS. For many, many years, it was embedded inside the propulsion track. And at some point, with of course, the evolution of air-breathing propulsion and the need for having a more dedicated Congress, it became its own entity. We have maintained that relationship for many, many years. So it's always good as the management is changing every 10 years or so to rekindle the relationship. So just as Frank is coming here today to talk to us and tell us about ISABE, I will be going there in 10 days to tell him about ICAS, and that relationship has been going on for a long time. Usually one year apart, so there is more time to prepare. It so happens because of COVID, we are coalescing a little bit. So maybe Frank would say a few words and then we'll sign, take a picture, and we can get straight to your presentation.
Yeah, first of all, good afternoon, everybody. Thanks for coming to this session. And thanks for Sarah and Dimitri for the introductory words. So I'm very happy to sign this Memorandum of Understanding, which you already signed, I see. You're fast, very well done. 3 times, apparently, and that is quite important for us because, as Dimitri said, ISABE came out of ICAS. It actually sort of not separated, it was always close, but it was actually sort of instigated as an own standing symposium in 1974. And since then, so since 50 years it's there. So we're doing the 26th Congress for air-breathing engines in Toulouse this year, in 2 weeks. And we are out of sync because of the quite significant interruption we all experienced in 2020, COVID, which brought us out of sync. We're trying to get back into sync in the next 2 or 3 years, and we will make sure that we then actually are back into that even and odd years working. So I'm going to sign this now. Let me do a handshake. Yes. And I can start talking, which I'm doing anyway. Good, here we go. Number 1, wherever that goes. Number 2. And number 3. That's your pen? Sure. We hold that up. Yes. And do a handshake thingy, isn't it? Sounds good. And somebody has a photograph. Yes. Good. So, the next test is whether I'm able to operate this wonderful machine here. So green might be to the right, and that might be a light. Good. Okay. So, good afternoon again. So, they asked me for the title of this presentation. I said, well, ISABE and the runway towards sustainable aviation has a certain nice tone to it. Let's try that. I must confess, I'm the head of propulsion for Airbus. But I'm here in my role as the president of ISABE, so I'm not talking on behalf of Airbus, just to be clear. You can ask me afterwards questions in my other role. I'm perfectly fine with that, but let's have that in mind whilst I'm talking. So, I decided we'd start with a bit of history, because maybe not everybody understands what ISABE is. I think Dimitri did a very good job in explaining that came out of ICAS in the early 70s to say, well, there's so much focus on propulsion, and sometimes the propulsion community actually gains from being in a smaller frame and having the ability to talk those things together. So on the 7th ICAS conference in Rome, it was decided, let's do something about it. And the year 72 was effectively the creation of this. In 74 it really kicked off. But you can see the 72 picture in the lower left of all the people who contributed to the first ISABE symposium. It's clearly actually demonstrates a reasonable size of people. Clearly not the 300, 400 which we normally have now at our symposiums. It's a little bit less than that. It clearly shows a huge number of diversity in terms of suit color and ties. Clearly you can see there are no young men, there are no colored people, there are no women in this group. So clearly the diversity of that group 50 years ago compared to the diversity we have today is significantly different. That's good. I think it's good that we actually develop further onwards and upwards in that respect. And the key thing is this symposium stayed together. It's somewhere in the midst of time, it named itself from symposium and sneaked in society for that S. And since then we are the International Society of Air-Breathing Engines, which of course has its prime purpose in making sure that industry, academia, research establishments and students come together in talking about the latest developments on air-breathing engines in terms of technologies, how to make them more fuel efficient, how to make them lighter, how to make them more reliable, and absolutely how to keep them safe. So the logic of us talking about ISABE and me talking here and Dimitri talking in about 14 days from now in Toulouse is information. Information about what has been done, what has been discussed on the ICAS Congress or on the ISABE Congress. And clearly, maybe actually the first thing, as you can see, we are currently a bit convoluted because the last ISABE conference was not 1 year ago, it was 2 years ago. It was in Ottawa, round about the end of September, as we always do, last week of September. And it was a small conference. It was just at the end of COVID, you could argue, about 200 people there. Lots of good technical talks about how to drive sustainability in aviation and what propulsion technologies are there. We had a good opening also with clean aviation, was represented by Jean-François Proucard, head of technology office, and showing what amount of money actually European investment is available for propulsion technologies of the future. And of course, we had also the appropriate NASA equivalents present. It was a nice conference, nice setting. You can see there the Parliament Hill of Ottawa. And as usual, ISABE lives from the keynote lectures and some targeted panels in between. And I thought, in order to give you a bit of idea, I selected a few of the keynotes. Sorry, that is a rather boring slide with a lot of words on it, but it might be a good talking point. So we looked at the fact that clearly, as a good understanding in the industry, and that was also brought up by Pratt & Whitney talk from Gene Thomason. It was about, look at electrical propulsion for the whole aircraft without any energy carrying source of like hydrogen or Jet A1 or something else will be limited to small aircrafts just because of the amount of energy you can get into a battery pack. That is a very obvious finding, but it's clearly then to say leading towards having more parallel hybrid propulsion concepts, having the link between either, so for smaller aircraft, the possibility of linking electrical powertrain with thermal powertrains is a very, very obvious choice, and Pratt & Whitney is doing some work in that direction in Canada, and he was talking about that. We were talking about small bore gas turbines and what can actually be done in terms of fuel burn, and we actually had earlier today also a quite nice session in this room around the potential fuel burn gains if you drive the course to higher temperatures and higher pressure ratios, which of course is the driver for the thermal cycle, for the Brayton cycle. And there is a territory of 5 to 10% fuel burn gain possible. And maybe for a moment with my Airbus hat on, I just remind ourselves in the industry as well, we have done this in the last generation of engines, whether it's for wide body or for single aisle. And clearly we learned as an industry that these engines need more tender love and care than the engine generation before. So maintenance and attention to maintenance of costs is quite important in all of this. So not only looking at the fuel burn, but also having an eye on what does it drive in terms of repair and overhaul cost, part cost, time on wing, and so on. So that's clearly an element. We had a discussion about that in Ottawa as well. We had MTU showing their wet concept, which is fundamentally a concept of collecting the hot gas stream after the gas generator, taking the air, which is fundamentally CO2 and H2O, as we all know, and sort of condensing the water in that hot stream again in a big condenser, and bring it back, bring it up to pressure again as in a liquid state, and re-inject it to the combustor. That is the wet concept. So you get a lot of benefit of having less sort of air to compress on the turbo machinery side and have the expansion in the turbine. Downside of that, of course, is drag and weight in the nacelle and the complexity of all of this. If you combine that with a high bypass ratio sort of engine, you have also the challenges of making sure that you don't have enough pressure losses or too many pressure losses in the bypass duct, because clearly the conversion of that pressure into velocity is the key. And so there's definitely was a lot of work 2 years ago. I think in the meantime it became a bit sort of colder, but it's still a concept actively worked by MTU, and we'll have to look where this is going. That is fundamentally, we could say, something like an advanced cycle. And the next bullet point I have here from CFM is much more an advanced architecture. So the advanced cycle is like, what can I do to the thermal cycle of the engine with, the re-injection and so on. It's one element of making engines better. The other element is, of course, propulsive efficiency. And if we go after propulsive efficiency, we all have learned in school that propulsive efficiency becomes one when I take effectively eternal amount of mass and accelerate it almost nothing. So we're going from something like bypass ratios or fan pressure ratios of 1.7, 1.6, 1.5 these days, down to lower and lower specific thrusts or fan pressure ratios. If you go down to territories of 1.1 or 1.05, you're very much in an area where you actually have an engine which would have a fan of the size of the fuselage of today's single-aisle aircraft, so roughly 3.5 meters, to give you an idea. Then to put a casing around this fan and a nacelle around this fan would completely defeat the object. So you can't do that. So you have to do it openly. And you could argue, if you look at that open fan or the RISE program of CFM, it is a logical consequence of actually the work which was started in the 80s with GE36 and the Allison and Pratt & Whitney sort of joint venture, where we were looking at open rotors, at that point counter-rotating, and then later on, about 15 years ago with Kroll, also counter-rotating. This now is a simplification. It's a single fan with a stator downstream, but no casing and no nacelle. Clearly, it has to have the ability to adjust the pitch in order to manage, on the one hand side, the performance challenges, the speed challenges, but also giving the ability to sort of give thrust reverse or at least a high amount of drag when you are after landing. So CFM talked about that. So that's clearly a very promising sort of activity, and we'll talk about that a bit later with some pictures. We had the clean aviation sort of 21 to 31 period with a huge budget of 1.7 billion euros, and sort of a real urge at the industry to sort of come and pick the right technologies, bet the right technologies for the future, and bring that into programs which we can do together. And a lot of that has happened already, and there are still calls ongoing. We're preparing the last call now, so that's quite good as well. That was myself. We spoke about our propulsion technology demonstration program at Airbus. So that was me, and it was more explaining why we're doing open fan as a demonstrator, why we're looking at hydrogen, what exactly we want to do there, and also where we are on SAF in terms of drop-in and non-drop-in SAF technology. And of course, we also spoke about electrification, which is not mentioned here. And then eventually sort of having in mind that we have to have the ecosystem getting along with the aviation industry, with the propulsion industry, to make sure that we are able to sort of not only sort of get, let's say, the most effective and efficient way of actually approaching a greener future or less carbon future for the aviation industry, have an ability to sort of look at that in terms of impact trajectories, climate drivers, and so on. And that was Steve Clark from Boeing presenting a cascade in that context the first time, I think, in Ottawa a couple of years ago. And I'm sure there was some talk about cascade also here on this conference. So that's so much about the conference 2 years ago. We have the next conference coming up in 2 weeks, as I said. I felt it would be good still to reflect in this audience, having in mind it's mainly the overall Council on Aeronautics with a lot of systems, operations, airframe, aerodynamics, CFD focus, some propulsion elements in there, to reflect on where we are. It's always nice to look at the impact of our industry on the society, what it does in terms of jobs, what it does in terms of connecting people. And of course, there's a lot going on. 4.5 billion passengers are sort of somewhat the number which we all quote. Clearly, we know in 10 years' time that can easily be almost double that number. We should have in mind it's still 4.5 billion passenger events. It doesn't mean it's 4.5 billion different people. It might be 1 billion people flying 4.5 times. So that's one element to look at. We have a lot of infrastructure around airports, especially when we start to change energy carriers, whether it's to the extreme, i.e. hydrogen, or not so extreme, drop-in or non-drop-in sustainable aviation fuels will be impacted. All these airports will be impacted, and we have to have them in the equation, in the tent, when we have the conversation of how do we project into the future. The airlines themselves serve about 50,000 different routes. There's about 25,000 commercial aircraft today doing those 50,000 routes. And it's quite a good loading factor if you can look at. So that is much better than maybe 20, 30 years ago in terms of how the airlines are capable of using the product we together all generate with the engines and the aircraft. Of course, the seat capacity is quite good with 82.5%. So in general, these numbers are numbers, but they also mean it's quite an important industry. It's still accountable for 2 to 3% of the CO2 in the world. That's not 20 or 30, but it's 2 to 3. But on the other hand, you also have the people in this room have a massive input and impact on these 2 to 3%. And that is quite important to have in mind as well. So let's look at how the engines are developing. I think I normally, not everybody in this room will be an engine engineer, so I might do some basics before we actually explain what are the technologies which are coming and why they're coming. That's a rather full slide. I start at the upper left, so you see a And if you forgive me, in my first life, I was chief engineer for the large engines at Rolls-Royce. So I took a Rolls-Royce engine. That's the Trent XWV 97, so it's about 100,000 pounds of takeoff thrust. And I only took it as an example just to simply explain what I used to call the 1/3 rule, because it makes it simple to understand what's happening. So if you look at a large turbofan like the 97K, it produces 100,000 pounds of thrust if the aircraft is stationary on the runway. At that moment in time, if it does that, it will actually burn about 3 kilograms of fuel per second. So that's quite an amount of energy. If you look at the caloric values of Jet A1, it's about 135 megawatt of chemical power which get released, or energy get released in that moment in time, in that combustor, and something happens with that. So, of course, that goes into the turbine system. The turbine system then extracts some mechanical energy to drive the compressors, about 45 megawatt to do that. So a third of the wonderful chemical energy I just converted is gone, because I needed it to get the process going in the first place, because if I do that at ambient pressure, it's rather boring and it won't do too much. So I need to do it at something like 50 to 60 bar when I'm on the ground. Then, of course, I have a second turbine system, the low-pressure turbine system, at the back of the engine, sort of sitting there and expecting another 50 to 55 megawatt from that hot gas, in order then over the LP spool, driving the fan, the large fan, which then takes 90% of the air, sort of pressurize it around the core, and go through a cold nozzle to accelerate and generate the thrust. So that's the other third gone. And then, of course, I have what we actually had earlier today, but also by somebody saying it's a perfect heat management. Then we do all the hot gases going out of the back. It's still generating some thrust, and it's doing the heat management of the engine. Because otherwise, we would have a lot of heat to manage and take away. So we don't need any extra cooling about this. So clearly, that's the gas turbine in a simple form, a turbofan engine. And you also all know there is a little picture in the middle of this plot where you can see different sort of different engine architectures and propulsive efficiencies. And of course, a simple turbojet gets better and better with speed, whilst a turboprop gets very good at low speeds, but then starts to decline, because fundamentally you have the problem that the swirl of the propeller is not necessarily directed back to axial direction, and you sort of lose efficiency. Also, you lose efficiency because you would have to run the propeller too fast, and you lose some transonics and shock losses. And the turbofan is somewhere in the middle between the two. And of course, nowadays we're starting to get at the limits of those things, especially when we're looking at our ultra-high bypass ratio turbofans to come, and also the open fan. And that's why I thought it would be good to have that sort of cartoon in the middle here to actually explain that. Of course, to drive the fuel efficiency, our engines get larger. We have all noticed that. So if you look at, for instance, a Boeing aircraft, 737, it's about 60 years now there. So in the mid-60s, it was developed. It had an engine at the beginning, which was like 53-inch fan, then a 63-inch fan. Now it's sort of 69 to 70. If you look at the 320, the competitor aircraft from this little company in the south of France, that is having sort of nowadays more in the territory of 78 to 81-inch fans on the aircraft, and before that it was 63 as well. So you can see the engines are getting bigger. At the same time, the core is getting smaller. We're having higher pressure ratios in them, and the temperatures are driving up. So what is that driving in technology requirements? We can have a very simple look. So we have, of course, in lots of the industry, in lots of the research establishments, in lots of the universities, people like the individual here on the left in the chart, who's actually doing very, very hard work on mixing the next superalloy. The next sort of thing we can do in terms of so nickel-based materials, CMCs, of course, coming with the need of environmental barrier coatings. Superalloys are coming also with the need of certain corrosion protection and so on. And over the last 20, 30 years, in the engine industry, significant changes were massively that you went from simple so-called single crystal alloys in turbines with complex cooling schemes to almost systems of blades. They won't survive anymore if they don't have internal coating, external coating, bond coating, thermal barrier coating, very, very finely driven ways of manufacturing the turbine blades, the intrinsic cooling schemes, the fan-shaped holes, all that sort of stuff. You can see the industry really actually fell over itself to try and optimize the system. And it clearly operates 200, 300 degrees above the melting point of the metal it actually is made out of, because it has so significant sort of materials, but also capability of managing these materials. We all know the picture on the right depicts a very simple turbofan. On the left, you see stuff is blue. On the right, so you see stuff is red. Typically, you go from aluminium, titanium, wire sort of simple nickel alloys to very, very complex nickel alloys and ceramics if you go from left to right through the engine. So a lot of the development and a lot of the discussion we have at the ISABE conference is around the details of that stuff. So how do we actually make a better compressor? How do we make better compressor material? By the way, the back of high-pressure compressors today is also nickel superalloys because the temperatures are in the territory of 700 degrees Celsius. It's very hot at the back of the compressor. So you compress air up to 60 bar, it's getting very, very hot. So you can't just have titanium there anymore. So that's quite important. Other things, of course, if you look at it, and maybe sometimes it's helpful to sit back. If you look at an engine like today, so whether you take any sort of modern turbofan, typically numbers, and we've seen some of them earlier on today on the board here, are in the territory of 50 to 60 overall pressure ratio. So you will have compressors in there, high pressure compressors, who have 20 to 1, 22 to 1 compression ratio. So there's a significant amount of compression, which means there's a significant amount of density change, which puts the biggest challenge into the operability and into the run-up of these engines. And that's why we all know we have variable stator vanes on these engines, because fundamentally, if I go from 60 to 1 or 20 to 1 sort of a compression ratio or something like a density change, so let's say a factor of 3 or 4 in a compressor, I have the challenge that if I run it up, at the beginning the density is everywhere the same and the front of the compressor is completely off design. So all of that needs to be accounted for, and that problem is getting more and more. The compressors are getting smaller and smaller. The back stages of our HP compressor today, just to give you an idea, might be as big as my finger, so roughly half an inch in that territory, so 10, 12, 30 millimeter. I thought I'd spend about 5 to 10 minutes on this slide. You can see it will be more talking than actually pointing, because it's a rather boring slide. But it has a significant question for all of us in it. Is the future the left or the right engine? And I'm sure there will be a lot of people in this room who have an opinion. I'm sure a lot of people in the room have an opinion for very, very good reasons. I have an opinion as well, and I can try to sort of rationalize that a bit with you. So on the left, you see a next generation ultra-high bypass ratio engine. Some form of bypass ratio, let's speculate 14, 15 in that territory. The fan clearly actually wants to run at a specific thrust or fan pressure ratio, which might be in the territory of 1.3, 1.35 in that one. So it's getting smaller. It wants to run slow. As it wants to run slow, it doesn't want to be connected to a 10-stage LP turbine, so it will be connected to a 4-stage LP turbine, which is running much faster than the fan. So there will be clearly a high-speed turbine at the back, which is running 3 to 4 times faster than the fan, in order to actually make the turbine run at its phase, so as fast as possible, and the fan at its perfect sweet spot, as slow as possible. Good for noise, good for performance, and so on. You will have to have a gearbox. Well, there are gearboxes in existence today. They work quite fine, so not a real problem. And of course, you still have a fan containment system, so you have a casing around it, typically out of titanium or some form of reinforced metal. Could be composite with some reinforcement as well. And then, of course, you have a nacelle and the classical sort of thrust reversing system, i.e. some form of trapdoor for the bypass flow to sort of go to the side and generate some reverse thrust after landing to help the pilots keep on the runway. So all of that is a classical sort of thing. And of course, I mentioned the sizes on a typical single-aisle aircraft earlier today. So we went from 53 to 63 to 81 inch. We might can go to 85, maybe 88, I don't know, in that territory. And then you start to sort of say, well, the aircrafts need to change, but it might be anyway when you do a new aircraft, you can do a bit different landing gear, make it a bit bigger. You can gull the wing a bit, so you can make it even bigger than that. But of course, you have then quite a significant amount of extra sort of bulky beast under the wing, and you have to manage the aerodynamics of the wing, and they're getting very sensitive if you're coming closer to the suction side. So you want to be careful with that. So that's the one option. I would call that evolutionary, because it's fundamentally doing what we said we're going to do, and just do a bit more of that. And now let's talk on the right-hand side. You see an example of an open rotor, an open fan. So it's actually the RISE engine I took here as an image, and that's a technology demonstrator for a different architecture. So what's the pros and what are the cons? So compared to the craw, or the old GE36 and the Pratt & Whitney Allison sort of open rotor, it actually is much more quiet. It is actually surprisingly quiet. That comes down to the fact that it's a bit simpler, but also down to the fact that there was a lot of advances in the aerodynamics and the ability to sort of design these blades. So, but that's, of course, a prediction rather than a fact. There's some tests, I think, the teams are doing in the background, which starts to show the right stuff, but it's a expectation. It's simpler, so you don't have to have any complex gearboxes, counter-rotating clapstrap, rotating oil systems, pitch control mechanisms, which actually sort of work each other. You don't have to sort of get air around that to manage the rather sizey gearboxes and so on, because it's fundamentally a single-stage fan as on the left side. It just doesn't have a casing and a nacelle. However, as it doesn't have a nacelle, it doesn't have the ability to thrust reverse the bypass flow, so it has to do something different. So it needs to be having some pitch control. It needs to be able to feather, because it's quite big. If you can't feather it and you have an engine failure in the core of the engine, for instance, the aircraft would be flying fairly sideways because of all that drag. So you need to be able to get the engine out of the way. So there's some complexity in it. There definitely needs to be a pitch control mechanism. There needs to be an emergency feathering mechanism, all of that sort of stuff. It then actually is also having a rather small core at the back behind a most likely even higher gear ratio gearbox. You all understand that if I do something like a 14-15 bypass ratio engine, I might be actually at 3-4 gear ratio. If I do a 60-70 bypass ratio engine, which you could call the thing on the right, I might be closer to 8, 9, 10, I don't know. So clearly it's a different gearbox, but doable. And the core itself is also small, but of course it drives a much more efficient propulsive architecture. So it might be not as hot as the one on the left, I don't know. So that's the sort of stuff to find out. And that's why the industry, I think, in its current phase, looking at it, uses this time to find out. And that's what we're doing. It's a lot of conversations in the propulsion domain, but also in the aircraft domain, about what to do. You know that there are different views on this in this room, in this country, in this continent, and over the continents. And so we'll find out as we go along. As me, and that's now me speaking as Airbus, we're pretty excited about this, about the opportunity to look at these options, because this propulsion, together with the wings, is the key thing you need for the next generation of aircraft. Those are the two things. All the other things are super important, but they're not that gearing into the fuel efficiency of the product. Wings and engines make the fuel efficiency of the product. So, what else did we talk about? In Ottawa, most likely here as well, and what else we are considering also then in Boeing and Airbus Isles or in Comac or in Embraer. So I don't want to make this a two-people show. This is a big industry. There is the question of hybridization. How much? Really? Is it efficient? Is it logical to do? The basic concept, if you are in industry, you learn to give elevator speeches, especially if you're an engineer, because you could meet your CEO in the elevator and you have to explain in 1 minute why you're doing this. So the elevator speech for hybridization is, it's an off-design optimization. We're doing so much on the aircraft and the engines to drive the fuel efficiency at cruise, or manage the challenges we had of takeoff and climb. To knit all of these things together in one architecture, it can help to bring some magic dust. And that magic dust can be electrification, can be using electrical energy in the right moment at the right time. The key question there is, do you build it in a way that it actually is, that you rely on it, that you have, maybe you could say, I help the compressor in spooling up from idle to full power and give it a bit of an electrical boost. And because of that, I can do the aerodynamics of the compressor differently. If you do something like this, you start to rely on it. Then your electrical motor needs to work, and it needs to work at the same reliability than the rest of your engine. But the rest of your engine has most likely 100 or 200 million flying hours as experience from the last 30, 40 years. Your electrical motor doesn't. So you're actually in that world of challenge. But you could also say, if I'm at ground idle or at flight idle, and I have the problem because my small cores and these big fans, which we have today already, are running reasonably fast, and unfortunately, in order to be stable and unmanaged, I'm already generating a bit more thrust than I wanted to, because I give more power to the LP system than I wanted to, but I have to do this in order to keep my core, my little core, stable, my little gas generator. The problem I then have to manage is, well, how do I get rid of that power which I gave to the LP system via the aerodynamics, which I can't put something like a barrier into the gas pass and divert the flow around the LP turbine. But I could go and say, well, I nick some of that power and put it back into the HP spool via an electrical motor generator. So it's power transfer from spool to spool in order to manage brakes on aircraft, or to manage descent slopes and consequently noise and other things. And that is definitely something you can do. And by the way, this is not safety reliable, essential, because if it doesn't work, the glide slope of the aircraft changes a bit at descent, and the flight management computer can know. And also the brakes are wearing a little bit faster out than you thought. So there are things you can do. So this picture shows all the possible areas where you could actually use hybridization. And what we're currently doing in the industry is talking about auto hybridization, which fundamentally means restrict it to the engine and just look at HP to LP spool power transfer for the right purposes. So you're typically talking about maybe 5–10% of the power maximum, much less sometimes, in order to actually manage this. Then you can start to say, you talk about micro hybridization, where you sort of say, I'm opening up power transfer to the aircraft. I bring sort of possibilities into the aircraft of managing and storing that power. I allow power transfer from the engine to the aircraft into that power storage, and I allow power transfer back to then, for instance, do takeoff boost, climb support, all that sort of stuff. But you very rapidly get into very heavy electrical systems on the aircraft side, which are expensive, and they need to be worthwhile. And fundamentally, that journey will continue. It's an interesting journey for all of us, and it will always be a question of what's the overall system benefit? Is it worth the cost and the weight you put in there, and what are the maintenance requirements of all of this? So that's an interesting element and rather exciting for all of us. And we should have in mind that in most of the world, this needs to be approached like design the system which does a reliable, meaningful step change in system performance of the aircraft, and then define, based on that, the requirements for all the components. What we're currently doing is a bit the other way around in a lot of the industry areas I'm looking at. People show, this is what I can do, how to make this work on an aircraft. And I think we need to turn that a little bit on its head. Yeah. So, I'm a propulsion engineer. I should help them. I did ask one member of my team, a rather gifted member of my team, do me a simple picture, image, which shows the importance of propulsion to the aviation industry. I think he definitely passed that one. And also show what our main aim is. How do we drive towards net zero? So clearly this little cartoon shows the propulsion engineer's aircraft will always have the engine in the center, and is of course very, very big. We love that. You have all the elements of the discussions, the public and the industry discussions in there as well. And to be fair, I put onto the title Engaging the Youth because I think it's one of the key elements of us getting to the kids in school, getting to the young people who are deciding what do I want to be in life, how they actually, as an engineer, can be capable of actually influencing how this industry looks like in 10, 20, 50 years from now. So that's rather important in my point of view. To be fair, there should be, of one of the tanks, there should be SAF rather than H2 just to get a bit more balance, but I left that one because it was such a nice picture. I thought I'm not going to go back to him and say, could you put something else there? But it has a nice element. So let's look at these elements. So what are we actually doing? So clearly the impact of new energy carriers is quite important to all of us. What does it do in the engine world? Why are we doing it? And so on. So I'm sure you will have heard, it's now day 3 of that conference, you will have heard a lot about sustainable aviation fuel. You all know it's a clever move to say, let's cut through the fossil fuel saga. Instead of using the stored energy from 260 million years ago, take the energy of today. And if you take the energy of today, you can say, I do some biostock type of or waste stock type of carbon sources and come this way towards sustainable aviation fuel, i.e. I use carbon hybrids of today, or I use the energy of today, solar, wind, tidal, whatever, and produce hydrogen. I produce electric energy. With the electric energy, I effectively produce hydrogen, and then I find a carbon source and Fischer drops myself a synthetic fuel. That's the other way of doing it. And most likely we'll have to do, if the clever people, much more clever than I am, have looked at this and said, well, realistically today, the world, these 25,000 aircraft I was talking about earlier, they are using about 340 million tons of Jet A1 to do their 48,000 routes around the world and carry those 4.5 billion passengers. So that's a rather big number of fuel. It's nothing compared to what is actually burned in cars and other things, but nonetheless, it's quite a big number of fuel. In 2050, with the growth expectation we have between 3 and 4%, that will be 500 million tons. We cannot do biostock for feedstock for 500 million tons of Jet-A1. It will not work. There's not enough land, which is, if you don't want to compete with food industry and other things, with feeding people. So you have to go down the route of actually bringing this partly biostock and partly synthetic fuels. And then you are in the world of saying, okay, so what do I do then? So if I look at these sustainable aviation fuels, do I make them that they fit to the Jet-A1 specification, which would be nice because we don't have to do anything. The engines run with it. The aircraft are happy with it. I don't have to worry about it. Or do I start to design that fuel that it is even better than Jet-A1? And that's almost a question which goes beyond engines and aircraft because it involves airports, it involves regulators, it involves a lot of questions because you then have to ask your question, so, okay, so if I bring that in, so I have a fuel which is almost Jet-A1, but not exactly Jet-A1, and I store it at an airport, how do I make sure it's not mixed with the other fuel? If I have an underfloor, under-apron sort of fuel line to the aircraft, can I pump SAF through the pipe where before that it was fossil Jet-A1 going through it? And so on. So all these questions come in, which gets you very rapidly into the question of how you bring that fuel into the industry. So do you start with drop-in and eventually phase out and then have the more designer fuels coming in? Because there are some benefits. The biggest difference between drop-in and non-drop-in might be aromatics, so the more lengthy circular molecule chains, which cause some of the smoke and non-volatile particle matters in the combustion process. But they're also quite helpful for older sort of engines and older aircraft, or stuff which is maybe now 10, 20 years old. Looking at the seals, the elastomeric seals, they get used to this type of stuff. If you then feed it with something which doesn't have it, these seals will get brittle, they will start to leak, and that is one of the things which we're looking at. So there's stuff in the aircraft and on the engine you have to check for fuel which isn't fulfilling the Jet-A1 specification. That's stuff which is ongoing, and that's more or less mentioned in the lower block here. So we're looking at the integrity of this, we're looking at the fuel gauging mechanisms and all of this. But fundamentally, 50% of this we could do today. It's no problem, so blending in. We're not doing it. It's very, very expensive, and it's not available at scale. And we have targets. The target towards the end of this decade is about 10% of blended fuel. So it will be interesting to see whether we achieve that target as an industry. And we will go further. So there will be an element of incentivization and penalization, taxation and incentivization coming, some price regulations and so on, in order to get to a point where you do this a bit more. We all drive cars. I think most likely 20% of the people in this room will drive electric cars today. But those who are not, fuel E5 or E10 at the fuel station very, very normally with ethanol and other things in there. So fundamentally, I think it's possible that we go down this route. It's a very meaningful route, but it's not the only one. We can, of course, also sort of look at hydrogen as an energy carrier. And in order to do this, I felt it would be nice to look at energy carriers overall. And what I plotted here is effectively the specific energy in kilowatt per kilogram and also volumetric. So the x-axis is effectively the kilowatt per kilogram, and the volumetric is on the y-axis. And I put some carriers there. And Jet-A1 is very much in the middle. By the way, nature has a very good long-range fuel as well. It's called goose fat. Goose fat is not far away from Jet-A1. And geese fly fairly long distances, so I think that's a good combination as well. I put here also where hydrogen is. Hydrogen is about 2.5 times higher caloric value than Jet-A1, or 2.8 times. It has the problem, it's not very dense. And you have to sort of either compress it or put it cryogenic in order to actually liquefy it. And then you get a reasonable sort of volumetric density as well, but you still are there and having to manage quite some challenges in terms of volume. And of course, you have a much heavier tank than you have today in an aircraft, because today you're using the aircraft structure as a tank. And with hydrogen, you will have it with some form of thermal flask in the aircraft. I also felt it would be worthwhile to look at power density and size of certain things. So I put a single aisle and a wide body engine there to give a feeling of how much power is actually on the fan. So 18 megawatt on a typical sort of 30,000 pounds takeoff thrust engine, and about 55 megawatt on a large aircraft engine. Power density is in the territory of 6 to 7 kilowatt per kilogram of the overall propulsion system. So quite a good machine, if you look at it. Very, very power dense. If you then were going back to the very beginning where we were talking about electrification and electric aircraft, if you go to an electric motor, 5 to 8 kilowatt per kilogram might be a bit conservative. You might go up to 10, 15 in that territory. But also, of course, the electric motors today, which are quite small if you look at them, but I haven't seen anything bigger than 1 or 2 megawatt. And going further than that is quite a challenge. So fundamentally, we should have in mind where are we in terms of orders of magnitude. What we're doing on single aisle or wide body aircraft is nowhere near what we're doing on, so it's literally an order of magnitude higher than what we can do with electric propulsion. And of course, a form of electric propulsion which allows a lot of range would be to go with a fuel cell. You could say, well, instead of having a battery, I do have a fuel cell. That fuel cell has a small tank of hydrogen which feeds it. I get the air from the outside. I do invert electrolysis and get fundamental electric power. I do a bit of DC to AC management, motor control units, electric motor, gearbox, propeller. I have a motor, I have an engine. Great. But of course also that has a limit of what you can do in terms of power density, and you have a lot of sort of stuff which you actually have to have in mind. So that's fundamentally where you are. So which just looking at energy carriers gives you an idea. Yes, hydrogen in terms of combustion of hydrogen is a very good source. In terms of using it in a fuel cell, it's a good source maybe for a smaller aircraft, for a regional aircraft and so on, if you actually do a multitude of engines. And, fundamentally, there's currently not a good alternative on wide body and single aisle aircraft to the combusting the energy carrier, I would say. What happens on fuel cell propulsion system is quite manifold. It's clearly one of the areas which is very exciting, and I think it's also the area where we get a lot of the new talent coming into the industry, and that's good, that's positive. And it's also positive to have these conversations on our conference, whether it's ICAS or ISABE. And so I asked my assistant to put a few images of the classical sort of candidates there. I think you all have noticed that Joby just managed to fly with a fuel cell, something like 500 miles, with this little sort of eVTOL. That's quite impressive, and it shows where, for small aircraft, literally general aviation or a bit bigger, that is an option. If you take such a system, maybe actually double, triple it in power density, link it to a turboprop, take 4 of them, you might have a regional aircraft which actually works in that way. That's the sort of stuff you can imagine and think of, but it doesn't mean that it will happen, because it also has to fulfill certain commercial sort of logics and other things. There's been a lot of activity ongoing with Universal Hydrogen, with Aeravia, Airbus itself. So my company is looking at fuel cell propulsion systems for the very same reason. We believe it's a viable thing to look at. It doesn't mean that it will happen in that form. But of course, there's a lot of stuff ongoing. It helps to engage the wider community and the society, and that's also quite important. The other role of international organizations like ICAS and ISABE is to form that glue between all these players, whether it's research establishments, whether it's universities, whether it's industrial OEMs and so on, whether it's people who are trying to sort of manage or are asked to manage public funds of the society to inject the right technologies for the next generation of transport systems, all of that stuff. And we fundamentally actually are playing that role. And I think you have seen that picture about multiple times. The only point I want to make, and then I think it's quite important to make that point, that ATAC target for 0E in 2050 has the classical technology, energy carrier, i.e. sustainable aviation fuels and operations in there. We should not forget that we're doing some of that today already by getting new aircraft into the market, replacing older aircraft which are 20-25% less fuel efficient, and consequently we are on that journey already by making this. So we have the ISABE conference in 2 weeks. If any of you feel like excited to come and see us in Toulouse, please come. We will be very happy to see you. We will be very happy to invite you for conversations about all the advanced power plant concept, the engine component designs, the fuels, the fuel implications, the fuel control systems, the fluid mechanics, and all the advanced material manufacturing stuff that people are looking at. We have some speakers. I think it's quite a good list of speakers. You will find some well-known names on there. We have all the major engine companies there as well. And thank you for your attention. I think I went a bit too long.
Thank you very much, Frank. So I think there is no time for further questions unless you have really one quick question. The first one who raised the hand could... Okay, can a question? Yes, it's coming. Microphone is coming. Is microphone coming? Okay, thank you. Okay. Sorry, I don't see very well.
So, depot level maintenance cost of an engine is very expensive, maybe $2 million, $1 million. Do you think that the new designs can address that? You talked about hybridization and fuel cells. Do you think that the new technology can lower the maintenance cost? Thank you.
It depends. I think the biggest lever you have on maintenance cost is driving the time between overhauls. That's on the traditional gas turbine ones. On the fuel cell electric propulsion, I think we will find out. Because I think on the fuel cell, things like membranes and other things will be the key thing which is wearing out there over time, or might be the stuff which is exchanging. And the industry has to find out. I can't really say in a logical sense. The fuel cell will be, for instance, on an overall propulsion system, about 20% of that propulsion system. So there is a chance that it might be actually not driving the costs too high in that respect.
So thank you very much. I'm sure that Frank will be available for further questions offline, let's say. And before leaving, I would like to invite one of our AIDA's members from the Italian Association of Aeronautics and Astronautics, who is providing a small souvenir from you, from AIDA.
Thank you very much.
So, you like it?
Yeah, roll the dice. Look at this. I can roll the dice now.
Yes. So thank you again, Frank. Thank you very much for your interesting lecture. And for the ones who will stay here or want to stay here or are still really interested in energy and propulsion, we will have 2 sessions here that will continue as parallel session. The first one will start in a few minutes. And there will be, I really suggest that you will stay until the end of the day, because we will have very high-level speakers after the coffee break also in this room. So thank you very much again.